Hello and welcome. I am Christian Buza, and in the next few minutes I would like to highlight some of our key findings about nearest neighbor regression, in particular about nearest neighbor regression in the presence of bad hubs. This study is a joint work with my co-authors Professor Nanopoulos and Gábor Nagy, and it has been recently accepted for publication in the Knowledge-Based Systems journal. In this talk, with regression, we mean prediction on a numeric scale. Regression tasks include, for example, credit scoring, estimation of the UPDRS score for Parkinson's disease patients, or prediction of the number of comments that a blog post is expected to receive. One of the most popular regression schemes is the nearest neighbor regression illustrated in this slide, in case of which the value of the target for a new instance is estimated as the average of the target values associated with the nearest neighbors. Although nearest neighbor regression is intuitive, simple to implement, and surprisingly effective in many cases, nearest neighbor models are affected by the presence of hubs. In order to understand this phenomenon, let us first observe that the nearest neighbor relationship is asymmetric. For example, the nearest neighbor of instance number 10 is instance number 2 in this example shown in this slide. However, the nearest neighbor of instance number 2 is not 10, but instance number 1. So, we can count how many times each instance appears as nearest neighbors of other instances. This quantity is denoted by nkx. That is, nkx denotes how many times instance x appears as one of the k nearest neighbors of other instances. For example, instance number 6 appears 2 times as the nearest neighbor of other instances. After computing nkx, we can plot the distribution of nkx. This is shown in the bottom of this slide. As you can see, in this example, there is one instance which appears as nearest neighbor of 3 other instances. Such instances, that is, instances which appear surprisingly frequently as nearest neighbors of other instances, are called hubs. The question is how such plots look in case of real data. This is what you can see in this slide. Most importantly, hubs are present in real data as well. A hub may be particularly harmful for regression if its label is substantially different from the labels of those instances for which this hub appears as one of the nearest neighbors. In order to study this phenomenon quantitatively, we defined high error instances, and we showed that there are hubs among those high error instances. The first Hubness-aware regression technique we proposed in this paper is a weighting scheme for nearest neighbor regression that ensures that high error hubs have reduced influence. This is illustrated in the next few slides, showing how we predict the label of the triangle using 2 of its nearest neighbors. The second approach we proposed is called error correction because it tries to correct the labels of high error instances. This is illustrated in this slide. We can, of course, combine the previous 2 techniques, which leads to our approach ECKNN. We performed many experiments on various datasets. Our key observations show that the proposed Hubness-aware regression techniques not only outperform nearest neighbor regression, but they are also competitive with many other regression approaches. Finally, I would like to express my hope that Hubness-aware regression will be applied in many cases, and I thank you for listening.